Hello. So in this tutorial, I will talk about CFD. What is CFD and how we use CFD to obtain results. So basically CFD is the abbreviation of computational fluid dynamics. So as you can see, the fluid. So we are talking about the fluid. The fluid comes gases, liquids. So we are talking about the fluid here. So CFD actually a method of obtaining the solution of the fluid equations, basically partial differential equations, for example, Navier-Stokes equations. And so which comes after solving the conservation of mass, conservation of momentum, and as well as conservation of energy. So from the CFD, we basically obtain the velocities and the stresses along in a system or a control volume. So like, for example, this is a control volume. So you solve for particular this control volume here and you calculate the velocities or stresses, stresses. So basically all this, so it can be solved by CFD. So before we go further, let's understand two important concepts which will, whenever you are reading a book or you're going anywhere, you want to know about CFD. So these two concepts will always come to you and you have tried to understand what actually that means. So let's understand some physical understanding of this important concept. First is Reynolds transpose theorem and another is substantial derivative. So what actually that means? First is Reynolds transpose theorem. So Reynolds transpose theorem says that rate of change of any property, any extensive property, is equal to the rate of change of that property in a controlled volume and rate of change over the control surface. For example, I have this infinitely small particle or a control volume. So change in this control volume, total any flow properties, for example, velocities, any changing in any, like for example, temperature is changing within this control volume. So change in this volume and change of this property over the surface. So total sum is equal to total rate of change of is the summation of these over the control volume and fluxes over the surface. So this is the basic definition. Reynolds transpose theorem states that the rate of change of extensive property n for a system is equal to the time of rate of change of n within the control volume and the net rate of the flux of the property n through the control surface. So basically this is what Reynolds transpose theorem is stating. So basically this part is called substantial derivative. Substantial derivative is total change, as we say, total change in a property. So which is can also, when in a, this is integral form, when we talk about the derivative form, so it can be stated like the change in a property per unit time is changes due to local condition, or you can say local derivative is convective derivative. So I will explain you the physical understanding. So basically this is substantial derivative. Substantial derivative is equal to the local derivative and the convective derivative. So what are these? Let's understand. For example, you have a fluid particle at time t1, it's here, and it moves in a very small time, like for example t2 tends to t1, to reach to the location 2 where the velocity are different. For example, here velocity is v1 and then velocity reach here v2. So the changes in this in this particle is mainly because of two conditions. First, because the values are changing intrinsic, because it's at that particular location, it's locally changing. For example, because of the fluid motion within this property, it will be changing. For example, we are talking about the change in density. So density, because of the fluid motion within this at T2, it is changing. Or when it is, we are observing this at T1 only, and this properties keep changing because of the fluid motion within here itself. But there is another, when it moves from here to here, the velocity is changed from v2 to v1, v1 to v2. So it means there is some change because of the its location as it moves. So this is the convective derivative. So let's say here, so d over dt is the time rate of change at a fixed point, and v dot delta is a convective derivative, is the time rate of change due to the movement of the fluid particle from one location to another location in the flow field, where the flow properties are spatially different, like v2 is different than v1. So basically, total change in, for example, the density is a change of due to local condition, and convective means it's change from the moving from one place to another place. So from because of the movement of the particle, and change within its where it is located or at a fixed point. Let's understand in a more physical way. For example, I will give the example of the what it is used by John D. Anderson in his CFD book, quite famous book. So for example, you are standing, you are on the mountain, and there was a cave. So what you say that there was a temperature T1 here. So you want to move, when you move here in cave, which is colder, here is temperature T2. So like T2 is less than, for example, T1. So you want to move here. When you move here at time T2, at T1, sorry, at T2, you arrive here. When you arrive here, so your temperature is changed because you change the location. The properties are different. At T1, T2 is different at the cave. But at the same moment, if your friend hit you a snowball, there's your friend, what he did, he hit you a snowball here. So your temperature, for a moment, your temperature is total temperature is decreased, which is basically is a local derivative. So change in locally for this moment. So that's it's called the local derivative. And from changing from here to from this location to this location is convective derivative. So convection. So change. So total change, for example, in temperature would be T over, sorry, Tt over At plus cause of velocity from here to this location. So this total change would be equal to this value. This is a substantial derivative. So this is all in this tutorial, and we will go further and we will use in when we solving the conservation of mass, momentum, and of course the Navier-Stokes equations, which is the heart of CFD.